We would now move on to the next speaker. Thanks again. Okay, so the next speaker, Chris, is he online?
I'm here. Yep.
Okay. Yeah. Hi. So yeah. So thanks a lot for joining, and it's a pleasure to have you here. Let me just introduce you briefly, then you can maybe start the talk, right?
Sure.
So Christopher Potts is a professor and chair of linguistics and professor of the computer science at Stanford, and a faculty member in the Stanford NLP Group and the Stanford AI Lab. His group uses computational methods to explore topics in emotion expression, context-dependent language use, systematicity and compositionality, and model interpretability. This research combines methods from linguistics, cognitive psychology, and computer science in the service of both scientific discovery and technological development. So Chris is going to speak on a very important topic, which is important for all of us: benchmark datasets, the essential resources on which all NLP depends. So over to you.
Thank you very much. I'm delighted to be here with you all. This is a really exciting event, and I just love the emphasis on data. As you can see, these issues are really central to my thinking these days. Just before I begin, I'll mention that I stashed a link to this talk at my personal homepage. I've got a lot of references to a lot of really interesting papers by lots of people. And if you want the full details on those, you'll find them at the end of the slide deck. Yeah, so my title is The Essential Resources on Which All NLP Depends. And you can probably hear that that's a play on a famous quotation from the oceanographer and explorer Jacques Cousteau, who said, "Water and air, the two essential fluids on which all life depends." And my comparison here is, of course, that in NLP, and in fact, throughout all of artificial intelligence, data sets are the essential resource on which all of our progress depends. So I find that an inspiring idea. Now, I should mention that Cousteau's quotation actually continues. He said, "Water and air have become global garbage cans." And some of you out there might be pessimistic enough that you want to extend my comparison into that very negative space. I'm more of an optimist. I think we've learned lots of interesting and exciting stuff about how to build benchmark data sets in our field. So I'm not going to go so far as to say they've become this polluted, but they are of such central importance that I think we should have in mind that things could get bad very quickly if we're not attentive to what our benchmark data sets really contain. Because after all, we are asking a lot of these data sets in NLP, and as I said, throughout artificial intelligence. Just think about the many roles that they're supposed to play. We use them to optimize models. We use them to evaluate models, to compare models, to enable new capabilities in models, to measure field-wide progress, and also for just basic scientific inquiry. This is pretty much the entire game here. So if we're not using reliable, interesting, important benchmark data sets to drive all of these questions, we're really deluding ourselves to think that we have solid results and have made progress. And that just reinforces the notion that benchmark data sets are absolutely essential. We live in good times for benchmark data sets, I feel. If you've been in the field for a few decades, you can think back to a time when we had very few data sets. And I'm reminded in this context of a quotation from Aravind Joshi, another explorer. This time we'll use analogies from the cosmos. Aravind said that data sets are like the telescopes of our field. And he actually worried at the time, which was about 2007, that we were behaving like astronomers who wanted to see the cosmos, but refused to build any telescopes. And I think he would be pleased at the state of the field today when we have more benchmark data sets than ever before. And that's giving us a chance to see what benchmarks are like when they exist in this field and in an era of really rapid progress. And that's an important thing about benchmarks that we should all have in mind, that they saturate faster than ever before. And what I mean by saturate is that we develop systems that surpass our estimates of human performance for those benchmarks faster than we ever have before. And let me give you a sense for this. So what I've got on this graph here is on the x-axis from the year about the 90s through to the year 2020. And on the y-axis, I have a normalized measure of distance from our human estimate of human performance, which is this red line here. So the first data set I'll highlight is MNIST. This is a famous data set. It was launched in the early 90s, and it took about 2 decades for that data set to be saturated, for us to see superhuman performance from a model. The switchboard data set is a similar story. It first appeared in the 1990s. And for the speech-to-text task, it took about 2 decades for us to have systems that were superhuman in this very rarefied sense that I'm using that term. The ImageNet dataset was launched in about 2009, and it took about 10 years for it to be saturated in this sense. And now what you're going to see is that progress is going to pick up really fast. So the SQUAD dataset came out in about 2016. It was saturated in about 3 years. Then we had SQUAD 2.0. It was saturated in even less time. Then the GLUE benchmark came out. GLUE continues to be important. And if you think back to the original paper, the authors actually say that they expect that this benchmark is so ambitious that it will take a long time before models do really well on it, when in fact it took about a year for us to see systems that were superhuman in this narrow sense. SuperGLUE was, of course, launched as an alternative to that. And it was supposed to be harder, but it again took only about a year for us to see systems that were superhuman in this very narrow sense. Now, I think it's perfectly reasonable to be a little bit cynical about what it means to be superhuman in the narrow sense that I'm using that term. I think that's entirely reasonable, but we should remind ourselves that these results would have looked like science fiction 20 years ago. We are talking about tasks, about benchmarks that many systems of even 10 years ago would have been unable to enter, to say nothing of achieving such astoundingly good scores. So maybe they're not superhuman, but this is certainly one measure of progress. The flip side of this, of course, is that when benchmarks appear now, we find limitations in them much more quickly than we ever did before. And to give you a sense for that, I'll just offer you a few comparisons across different data sets, starting with the famous Penn tree bank. It appeared in 1993. It continues to be used to this day. And this timeline here with these red dots are identifying papers throughout that time period that identified errors in the Penn tree bank. And you can see that there are relatively few of them. They all come from a few groups. This is really important work of finding errors, and you might have a suspicion that if more effort had been placed on finding these errors, we would have found even more of them. Now let's fast forward a little bit to the Stanford Natural Language Inference Corpus. It appeared in 2015, and right away, you have an outpouring of papers identifying shortcomings in that data set. And it's not just errors in this case, it's also things like artifacts that derive from the data set creation process, and also instances of really problematic, pernicious social biases, in addition to errors, of course. SQUAD appeared 1 year later. And again, you get a bunch of papers, in this case, talking about artifacts and related shortcomings right away. It's very different from the kind of easy life that the Penn tree bank got to lead for a very long time. One more point of comparison, this one is kind of interesting. I mentioned ImageNet before. It appeared in 2009. And for a while, it got to lead a kind of quiet life as a standard sort of benchmark like the BTB there. But then, of course, the times are changing, where we've reached a really introspective moment when it comes to thinking about data. And so in more recent years, you get, again, an outpouring of papers identifying different kinds of shortcomings in that data set, not just errors, but also things related to artifacts and social biases. And this seems kind of inevitable as we think more about benchmarks and we're more ambitious in creating them, we're also going to find their limitations more quickly. So here are my central questions for today. There's a lot we could think about when we think about developing reliable benchmarks for the field. I've picked just a sample of them, and if anything, that might just inspire you to think about additional issues we can discuss. Here's my quick rundown. First question, should we be relying on naturalistic data, or should we be relying on crowdsourcing, which would be more controlled? Now, my answer here is that we should use both. I think there is value in both kinds of methods, and so we should be making use of both of them when we think about developing new benchmarks. What about adversarial examples? Should we collect data sets that we know are really hard for our models, or should we be looking to benchmarks that contain more of what you might call the common or average case? I've been a proponent of developing adversarial data sets in the past, so I certainly think there's value there, but not exclusively. Again, my answer is going to be both. Both of these things clearly have real value for us. What about synthetic data sets versus naturalistic ones? Now here, I think almost everyone in the field believes that naturalistic benchmarks have an important role to play. So what I'll be arguing actually is that also synthetic data sets could play a role, an important analytic role. And so there's a place for them as well. I hope you're not worrying that I'm being very wishy-washy here and giving all these both answers. This is really just about embracing all of the exciting new methods that we have. Maybe there'll be some twists here. Let's look at another one. Should we be doing human tasks for our benchmarks or what I'll call machine tasks? And here you might think, certainly we should be doing only human tasks because that's the really important thing that we're all striving for. But again, in what I hope is a little bit of a twist, I want to say that there's going to be value in both kinds of methods here. Final question. Leaderboards, we're all driven by them. They control our lives as professionals. Are they good or are they bad? Here, I hope you're kind of thinking that I'm going to say they're purely bad, but no, actually my twist is that I think that they have both good and bad aspects. And so there you can see it's just about figuring out how to weight those two kinds of opposing things when we think about the roles that leaderboards should play. So that's a quick rundown, and let me now dive into each one of these in a little bit more detail. Starting with this question, should we be relying on naturalistic data or relying mainly on crowdsourcing, which would be more experiment and laboratory driven? And the fundamental reason that I give a both answer here is that I think this is really about trade-offs. I think both of these things have important things to contribute. What I mean by a naturalistic data set would be something that you found and maybe curated. So you could scrape something from the web with all its metadata, or just use a found database or something like that, something that was not collected primarily for developing NLP models. On the plus side, I think this data is likely to be abundant, pretty inexpensive to collect, and also genuine in the sense that it was created for some other purpose beyond just helping us in the field. And those are certainly positives. But we could balance that against some clear negatives. So the data will likely be uncontrolled in ways that you don't fully understand. It's likely to be limited to things that are naturally occurring, which could really limit the kind of analytic questions that you could pose. And of course, we might worry that because it's found and curated, it's also intrusive and maybe not privacy preserving in the way that we would like. Contrast that with crowdsourced data set. This would be like something lab grown where you have people do controlled tasks. Here, it's going to be very controlled in terms of the data set. It's going to be privacy preserving because we can opt in participants and even let them opt out. And it's also likely to be very expressive because, of course, you could have people do very unusual things as part of your crowdsourcing task that really provide you with something like exactly the information that you're looking for. There are clear negatives as well. Of course, it's likely to be scarce and very expensive to collect. And it also might have a contrived aspect, which might go hand in hand with it being very expressive. Your task might be very unusual and not naturalistic in ways that we really value. But there's good and bad in both of these things. And what I'd like to highlight is this trade-off between being genuine and being expressive. And the question would be, can we develop methods to create benchmarks that will have both aspects, that will leverage the good from both sides of this? And I think we can. And let me give you one example from a recent project that I've been involved with, which is called the DynaSent project. And that stands for dynamic sentiment. And you'll see why it's dynamic, because we imagine that it's going to have multiple rounds over the course of its lifetime. For DynaSent, we start with what we call model 0, and this is a big sentiment model that we train on lots of existing sentiment benchmarks. Model 0 is primarily a device for us for finding challenging, naturally occurring sentences in the Yelp academic data set. So this is going to be naturalistic, found and curated data. And what we do there is a simple heuristic, which is we say if the model predicted positive, but the example occurred in a negative review and vice versa, it's probably a difficult case and one that we would specially value. That's just a heuristic. We then run that through a human validation pipeline, and that gives us our round 1 data set. The round 1 data set is now used as a kind of engine to develop a second model, which is another big model that we train on a lot of existing sentiment benchmarks combined with our round 1 data. And now what we do with model 1 is use it as a device in a crowdsourcing experiment where we have people interact with model 1 and try to fool it. And in this case, we're using crowdsourcing methods to create new examples that we know will be difficult for this very good model 1 that we developed. And an important thing about that, which I want to linger over in a moment, is that we actually prompted these crowd workers with existing naturalistic sentences and had them edit them. And we think that that increased the naturalistic flavor of the examples that were lab grown as part of round 2. That's fed through the same human validation pipeline, and that gives us the second round of our data. And I've given over here in the corner of the screen some details on the splits. There's a lot of different ways you can think about DynaScent. And I think that those play off the fact that rounds 1 and round 2 are different in this important sense, with round 1 being more naturalistic and round 2 being more controlled in the sense that we're having these crowd workers try to fool a very good model as part of creating the data set. And I really want to emphasize that the prompt thing helped us a lot for round 2, where we're having people write original sentences from scratch. We found that when we gave them these prompts, they used them and they made minor edits by and large to create their new example that fooled the model they were interacting with. It also led to examples that had more, that were longer on average and had a greater vocabulary on average than the condition where we didn't give people these prompt sentences. And really what I think we've done here by giving them naturalistic prompts is free them from the very difficult burden of having to do creative writing as part of one of these crowdsourcing efforts. Instead, what they had to do is taking an existing naturalistic example and modify it to get the job done. And that led to some really exciting examples that I think we would not have seen in real quantity if we had just been using the round 1 method of harvesting these examples. For example, just to pick one kind of systematic pattern we see, people hit upon the strategy that if they shifted perspective in their example, they could pretty easily fool the model. And that led to a lot of examples like, my sister hated the food, but she's massively wrong. Or maybe more facetiously, breakfast is really good if you're trying to feed it to dogs. I love these examples. I'm sure they're out there in the wild for us to find, but the crowdsourcing effort really gave them to us in a lot of density, and I think that's very exciting. Let me move to my second topic now, which is the question of whether we should be using adversarial examples or just relying on kind of average case examples to build up these benchmarks. And you can see that I'm in favor of adversarial examples. That was part of the DynaScent project. But there are voices out there saying that we should really be focused on the most common cases when developing benchmarks, and the adversarial ones might lead us astray. Again, though, I'm giving a both answer. I think there's value to both of these things. Just to sketch this out a little bit, let's just say that the standard approach is one where you create a data set from a single model independent process and you divide it into train, dev, test. The adversarial case, which was introduced a few years ago and has been really exciting in terms of marking progress, is subtly different. Here you have a separate test set that's created in ways that you suspect or know will be challenging given the system you've developed and the data that it was trained on, maybe in the standard way. That's adversarial assessment. And then we also have now, thanks to the DynaBench platform, full adversarial data sets. These are data sets where the train, dev, and test were all guided in some sense by attempts to fool a model or set of models that we think are top performing. So this is the landscape here, and I think all of these things have been really fruitful. I should mention here that I'm using the word adversary, but that might be too strong. I think there are a number of flavors of adversaries that might be useful to think about. We could have the simple inquirer who just poses systematically a bunch of examples as part of an assessment to try to figure out whether a model has acquired a certain target capability, like it knows about antonyms or something like that. We could also have the challenger, and this would be where, based on something that you know about the training data, you're pretty sure that you have examples that are going to fool models that were trained on that data. The frenemy would be someone who is really truly adversarial. This could be like the crowd workers that I mentioned from DynaSet. They're trying to fool the model, but they're doing it for the goal of developing better systems as we work with their examples and train systems on that basis. And then you could contrast that with a true adversary. This could be someone, a kind of black hat hacker who is actively trying to concoct examples, not even close to naturalistic, that we know will fool top performing models in ways that could lead a deployed system to perform very badly, for example. All of these, I think, have their role as well. The DynaBench platform was part of the engine for round 2 in our DynaScent project, and it's led to lots of interesting data sets. This is an open source platform that makes it very easy for us to run tasks where crowd workers interact with a model to try to fool it. Here's a rundown of the DynaBench-based data sets that I know about, and I think more are about to hit the market soon. And the result of this is that we've learned a lot about the dynamics of these adversarial data set projects. And I think that's leading to stronger models. And I'll try to summarize that evidence in a second. I do want to mention though, so I'm coming down on the side of saying that both of these approaches have their value and we should be making use of both of them. I think there is a counterpoint there in a recent paper by Sam Bowman and Dahl, where they kind of say that adversarial dataset collection maybe is not the way to go and we should focus on the average case. And here are two important quotes from the paper. First, they just say that adversarial examples are not a panacea. Adversarial filtering can systematically eliminate coverage of linguistic phenomena or skills that are needed for the task but already well solved by the adversary model. This mode seeking, as opposed to mass covering behavior by adversarial filtering, if left unchecked, tends to reduce dataset diversity and thus make validity harder to achieve. I think they're actually absolutely right in this quotation here, but what you can hear in this is that we should be pleading with them to make use of both methods, because I think adversarial examples have their place, but I wouldn't rely on them completely because I agree that we want examples that will kind of coverage the average case, the mass covering that they're referring to here. But that's not to say that we don't want to push on these models to make sure that they can cover the long tail of very intricate and difficult things that are rare in the world, but that humans make sense of very easily, and therefore our models should as well. There's another quotation from the paper that I want to highlight here, which is that they seem to be saying that standard evaluations are sufficient for the kind of broader goals that they've set for benchmark dataset creation. This position paper argues that concerns about standard benchmarks that motivate methods like adversarial filtering are justified, but that they can and should be addressed directly, and that it's possible and reasonable to do so in the context of static IID evaluation. That's like a push for the standard approach that I mentioned before. And here again, I would just say first, we don't have to be filtering. Our data sets could consist of examples that are adversarial and those that are not with respect to some class of models. And I just really want to emphasize that there's value in having both kinds of examples in the data sets that we create. And just to make that vivid for you, just think on the job to be done here for these benchmark data sets. We want, of course, that the models we create with them can handle the average case, like for sentiment, the food was good. But we also need these models to handle those very difficult cases that our crowdsourcing effort uncovered for Dynasend, examples that are rare in the world, but very intuitive for people to make sense of. That's the complete job to be done. And you can see why I'm pushing for a both answer to this question, because the average case benchmarks might handle case zero, and we might need the adversarial methods to really get good coverage on things that are like 1 through 3 and all the other kind of things that are out there that we don't fully know about, but that could surface as part of adversarial dynamics in a benchmark data set creation effort. That's another one with an interesting neologism. So here are the major lessons that I think we've learned so far from developing data sets that employ both of these methods. First, it's just true that top systems have often found unsystematic solutions, despite maybe even being superhuman according to our metrics. And that's something that adversarial assessments have shown us really clearly. However, and this is really important here as well, progress on these challenge sets seems to correlate with meaningful progress in the field. For example, for natural language inference, many of the challenge sets were launched before the BERT models came on the scene. And those challenge problems looked really difficult for the models of the day. And now you can find that simple fine-tuning of a model like BERT solves those challenge data sets. And that seems like a real mark of progress that these larger models that many of us are working with are actually able to accommodate the long tail of very difficult cases as well as the average case ones, right? This is important. Present day systems can get traction on these adversarial cases without degradation on the general case. If this weren't true, if performing well on the adversarial examples was always at the expense of the average case, it would be worrisome. But since it's very clear that these systems can do both, again, that gives me a both answer to the overarching question of which methods we should be using. And finally, and this is really important here, even if you set aside developing better systems, the role for adversarial examples could be just helping you prevent a really embarrassing thing from happening in the world, which is that you deploy a system and people find simple cases, intuitive cases where it fails, and those cases define public perception for your system. It seems to me like it's just smart to use some measure of adversarial assessment to prevent that very negative outcome. All right, my third question here. Should we be using synthetic benchmarks or naturalistic benchmarks? And as I said before, I think everyone agrees that there's an important role for naturalistic benchmarks throughout AI. And so what I really want to do here is argue that there could also be a place for synthetic data when we think about the stock of benchmarks that we're all relying on. And here's the central piece for that for me. When we work with naturalistic data sets, it's really important to keep in mind that probably both the data set and the model that you're exploring are unknowns or partially known in the experimental sense, right? Think about the standard recipe. You have some naturalistic data set, and you have very partial understanding of what that data set contains because it's a huge sea of examples you harvested or examples you crowdsourced. Using that data set, you're going to now train a model. And maybe the point of doing these experiments is that you don't fully understand what that model is capable of or how it works. So you put these two unknowns together and you get some output, something happens, maybe a mistake is made. And the question is, where do I assign blame for the mistake? Does the problem lie with the model or with the data set? Now, given that both of them are unknowns, it might be very difficult for you to offer a confident answer to that question. But if the data set is partially synthetic, you can probably fully understand what it contains. And now the mistake is either easily traced to the data set or something that you might explore as a shortcoming of your model. And again, let me make this vivid with a little bit of a story here. So especially for natural language inference, we have a very intuitive set of learning targets that come from kind of logical semantics. And one of them is just this intuitive learning target that if sentence A entails sentence B, then not B entails not A. This is the famous reversal of entailments that comes with classical negation. So let's imagine that's our learning target. And many people have set it as an important learning target. And we have this observation that top performing NLI models often fail to achieve this learning target in the sense that models trained on the big benchmark data sets have not learned this fact about negation. A tempting conclusion here would be to say that those top performing models, for whatever reason, are incapable of learning negation, using this observation, this set of observations, as evidence for that claim about models. However, importantly, we now know that those benchmarks severely underrepresent negation. And so as soon as you say that, you realize that the observation we made about failing to achieve this learning target might not be a problem with the model. It might just be a fact about the data set, which might not even fully and unambiguously specify what the learning target for negation might be. And I actually think that that's precisely what has happened with this particular case. So to address this question, in my group, we developed what we call the monotonicity NLI data set. And I've called it a slightly synthetic data set for reasons that I'll make clear here. So for the positive part of the data set, we started with an SNLI hypothesis, like the food was served. And then we, as analysts, looked up using a resource like WordNet, a more specific form of food like pizza. And we used that to create this slightly synthetic example, pizza was served. Having done that and assuming the soundness of WordNet in this case, we can now fire off two examples, A neutral B and B entailment A. And then importantly, we have a second half of this data set called negative MoNLI. The only difference here is that now we start with negated premises from SNLI, perform that same WordNet substitution, and now we apply the monotonicity rule and we get two examples, but now with the entailment pattern reversed. A entails B and B is neutral with respect to A. We use this first as a challenge data set with a little bit of fine tuning. And here's the full story here. So we have a few models, so two pre-BERT models and one BERT model. They have their various forms of pre-training, and they were all trained on the SNLI benchmark. And let's focus in on that BERT row there. So BERT does really well on SNLI at about 91. It does extremely well on the positive part of our data set, suggesting that it knows something really interesting about those lexical relationships. But for the negative part of our data set, it plummets to 2.2. It's very clear here that what the model has learned to do is simply ignore all the negations in our negated examples. And so you might think, oh, this is really despairing because BERT has just failed to acquire any information about negation. However, with only a very modest amount of fine tuning on our negative examples, and with very careful splits to make sure that the model is still being asked to generalize in very challenging ways, we now can boost the performance of that same BERT model to 90 on the negated examples without really any degradation in performance on SNLI itself or on the positive part of our data set. So the overall lesson here is that it was a failure of SNLI, not the models, that led to the models being unable to handle negation. And as soon as we solve that data coverage problem, those models perform really well on our learning target, right? And here's the bottom line. This was all possible because of the slightly synthetic data set that we created. And what we've learned here is that when we turn back to a naturalistic benchmark, we do so now knowing two things. First, BERT can in principle learn negation. Just gave you a kind of existence proof of that. And we also know that data coverage will be a major factor in whether or not that learning target is realized. On to my fourth question. This is a little bit trickier, but I still want to give a both answer to this. Should we be relying on machine tasks like simple classification things, or should our benchmarks move to the kind of more open-ended interactional things that we find from actual human life and human interactions with language? And again, what I want to say is there's value in both of these things, maybe for the long term. But there is a kind of thing that I worry about a lot with the way we pose these benchmark tasks, and the way, in particular, the way we estimate human performance on those tasks, which is in a very kind of machine-oriented way. Just to give you a sense for how vexing this could be if, say, you were a crowd worker, let's think about the NLI labeling case. So imagine that you're a crowd worker and you're given this pair of sentences. The premise is a dog jumping, and the hypothesis is a dog wearing a sweater. You might say, okay, that's clear. I read the guidelines. That's a neutral example. What about turtle contradicts linguist? You think, well, I can imagine a possible world in which there are turtles that are linguists, but I was told this was kind of about common sense reasoning, and no turtles in our world are linguists, so I'll give this the contradiction label. So far, so good. Okay, what about a photo of a racehorse and a photo of an athlete? Here you might really be wondering about whether or not any animal could be called an athlete, right? This is a kind of point of lexical uncertainty, and it seems like there's no simple fact of the matter. And if we were humans interacting about this question, we would certainly have some kind of discussion about whether or not animals can be athletes. But here you're a crowd worker, and so you just got to guess. And so maybe you say entailment, and somebody else guesses differently, and we register that as some point of uncertainty. But in the end, we're going to infer a single label for this, and that label might obscure this important point of variation that I just identified. Here's another example: a chef using a barbecue and a person using a machine. You say, okay, I'll buy that every chef has to be a person, but is a barbecue a machine? It really depends on what kind of job you've posed and what you mean by these terms. Again, let's discuss and debate. But what we actually do with these crowd workers is force them to make a single label choice, because we know that that's the kind of thing that our models need. But it's certainly not reflective of the human capacity to think about lexical ambiguity and uncertainty in the context of entailment, right? So this is the important thing. Humans would say, let's discuss. And now you can see that when we say human performance on some benchmark, we're actually talking about like average performance of harried crowd workers doing a machine task repeatedly with no chance for discussion and debate, that very human thing. So this is a point of real concern, I would say, and it might be distorting progress on this and other problems. A very common response here is to say, hey, let's leap all the way to the other end of the spectrum here. Let's just run Turing tests, right? Because a Turing test is a kind of very human thing. I mean, there were some concessions to the machines in this case, like they don't have to be embodied, they just have to have conversation. But beyond that, humans are really allowed to do anything, including, of course, discussion. So you might think, let's have our evaluations be more in that mode. The problem in particular with the Turing test is that humans are really not good participants in it, and they fail in both directions, right? So in the first Turing test, for example, one of the people was repeatedly misclassified as a machine in virtue of the fact that she knew a lot about Shakespeare. And so that's one kind of failure. Another kind of failure is that people are very susceptible to cheap tricks that lead them to believe that even very simple systems are human. And one of the more recent Turing tests with this AI, Eugene Gustman, is an example of that. And we don't actually have to go all the way to the Turing test to think about how these evaluations could go wrong. For example, you can find on the internet recordings of people interacting with Google's tool Duplex, and those people routinely fail the Turing test in the context of their interactions with this system. And even more down to earth, you could think about, for example, natural language generation and all these papers that are emerging that show that even crowd workers can't really tell whether a given sentence was generated by a big language model or a human. And that's a very narrow kind of failure of the Turing test, I would say. So we can't swing all the way in that direction, but surely there are some interesting points in between these two extremes, right? So we have these standard evaluations, which really pose the question, can a system perform more accurately on a friendly task than a human performing that same machine task? This certainly has a role for our field because it's scalable, and it's objective, and it's easy to kind of have these questions posed field-wide, and all of us to participate in answering the question for various systems that we're developing and questions we want to pose. So I think that has value, but it's not going to tell the whole story because it's not a very human thing to be doing. And again, we could leap all the way to the Turing test at the other end of the extreme, but there's so much interesting place in the middle here. For example, we could ask the question, can a system behave systematically, even if it's not accurate? This would be more like keying into human notions of systematicity and compositionality in the meaning sense. Can a system assess its own confidence, know when not to make a prediction? This is a really challenging task in metacognition that we could pose as a first order goal for the systems that we developed, reflecting its importance in human cognition. Or can a system make people happier and more productive, right? I'm kind of optimistic about this because nobody really needs to run a Turing test, but many people have questions like happier and more productive for systems that we deploy out in the world. And you can imagine a day where so many of those assessments are being run that they can actually become primary assessments and take some of the weight off of the standard mode that we're also locked into now, partly as a result of convenience. Final question here, leaderboards, are they good or bad? And I think a lot of us think that they have bad elements to them, but we continue to rely on them and think about them and participate in the leaderboard culture that we're all part of. And partly what I want to say to you is that that has many good aspects and you should not feel so ashamed. And what we should really be looking for is an opportunity to build better leaderboards that will engage deeper questions for us so that they can be even better than they currently are. But even in their present state, I think they can be a force for good. But let's start to balance the good and the bad here. Kind of the crux of it for me, the overarching issue is summarized in Strathern's law, which says, when a measure becomes a target, it ceases to be a good measure. If we all get overly fixated on one benchmark or set of benchmarks, we will mistake progress on that benchmark for progress in some broader sense, and we might be deluding ourselves by making that kind of inference. So that's something to be worried about. But there's clearly good elements to this. And if you've participated in scientific fields outside of the hardest of hard sciences that don't have leaderboards, this might really resonate with you. Leaderboards provide an objective basis for comparisons, and in doing that, they create opportunities for wild-seeming ideas to get a hearing. If you have some very unusual idea about a model, and a priori people say that that seems like a bad idea, but you do well on a leaderboard, people might pay attention to you. And that really contrasts with fields that don't have leaderboards, where the only kind of assessment that you might get might be from peer reviewers. And if they're closed-minded about your contribution, that might be the beginning and the end of the conversation. So the leaderboard could clearly be a force for good in allowing wild ideas to get a hearing. But there's plenty of bad things here. And a lot of this has to do with the culture and the way we think about and talk about leaderboards as measuring tools. So some bad things are, first, we get conflation of benchmark improvements with progress, right? Whereas I think we all kind of know that doing epsilon better on glue does not necessarily mark progress. We should be aware also that even a large gain on glue might not correspond to anything like progress for the true goals that we have, right? Because we don't want to run afoul of Strathern's law here. You also get a common conflation of benchmarks with the empirical domains that they're part of, right? So you get newspaper headlines that say things like squad is solved, or sorry, the newspaper headline might say question answering is solved. And we all know that what that actually means is that some system performed better than our artificial measure of human performance on the squad data set. If we say question answering is solved as a shorthand for that much more articulated and narrow claim about the world, we're really kind of confusing ourselves and certainly confusing people outside of our field who might not be sensitive to all the nuances of the difference between a benchmark and the wider area that it's part of. And that relates to this third point here, which is that benchmark performance doesn't necessarily mean that you're doing better in terms of progress on the capabilities that we actually care about. We have to keep that in mind. And we should make sure that we don't talk about benchmark results in ways that would muddy the water around these issues.
Hello, Chris.
Yes, go ahead.
Yeah, sorry to interrupt. So we need to complete your talk in the next 3 or 4 minutes. So yeah.
Oh, I see. I started late, so I thought it would be okay.
Sure,
you
can take 5 more minutes, I guess. Sure.
Okay. Oh, 5 more minutes is fine.
Yeah, sure.
Okay, that's plenty. Yep. There's just one more thing I wanted to say about leaderboards, which is let's accept that they exist, the good and the bad, and think about how they could be better. And one thing that's really important here is that I think we should make our leaderboards more multidimensional so that they can be more tailored to the actual things that we want to measure in the world. There are a bunch of really exciting efforts out there to develop software systems that will actually help us meet those objectives. DynaBench, which I've mentioned a few times, is one example. DawnBench and Explainaboard are also attempts to offer us leaderboards that could be tailored to specific goals that we have. And because I know it best, I'm going to talk about DynaBoard. I think this is very intuitive. Let me just give you one example of how we could have a dialogue around the leaderboard as opposed to just accepting it at face value. So what I have here is a bunch of results for question answering systems. Those are given along the rows here. And the way we're working is that we've allocated most of our scoring to performance. We really care about that F1, for example. But we also have a bunch of other things that we're going to measure: throughput, memory, fairness, and robustness. And I've given those all equal weight here because maybe I don't yet know how I want to weight them differentially. And that leads to a set of DynaScores that are over here on the right. And the Duberna model looks best according to this particular weighting. And this might be a kind of null starting point. But now imagine that instead you're in a context where you really care about fairness more than throughput, memory, and robustness. So you boost the amount of value that you're going to give to that particular metric, also valuing performance above all else. Now an interesting thing has happened. Electra large is the better choice here, and the Duberna model is in second place. And of course, you can imagine that as we think about and motivate different weightings for all of these different metrics, we might end up valuing very different models as a result. And I think that's exciting because it could mean that the metric is part of the overall proposal, and it might be very tailored to the particular goals that the analysts have or the people deploying the system have. So in summary here, just quickly for these leaderboards, at present, they tend to be one-dimensional, F1 and accuracy and things like that. And as a result, they're not sensitive to the context or the use case that's being addressed. And of course, we set the terms entirely as the research community. And that means that we built all of these things around machine tasks and not human tasks. But I think we're headed into an exciting world where leaderboards could be much more. They could be high dimensional and fluid. And they could be fluid in the sense that they could be sensitive to the use case and the context. And the terms of the metrics, like the DynaScore weighting, could be set by the stakeholders. And in turn, we could build them more around human tasks. We have the analytic techniques. There are going to be some culture changes necessary to achieve this, but I think it's possible and could lead to lots of exciting new notions of progress. All right, and let me wrap up here. I began with this observation that benchmarks are the essential resources on which all of our fields depend. And I posed these central questions and I gave motivated but wishy-washy answers to all of them. I think all of these methods have value and all of them should be used and allowed to interact with each other as we develop more and better benchmarks. And of course, just to plant some ideas in your head, of course, this is by far, far from being the only questions we could think about. We could also think about disclosures and the importance of them in understanding our benchmarks. We could also think about how we're going to achieve cross-linguistic coverage for benchmarks, given that now most of them are in English. We could think about statistical power, and of course, all of us are worried as dataset creators and model developers that our systems will embed pernicious social biases, and it's important to think about how we could get out of that trap. And I'm sure you can think of other issues that are important for us to think about as we go off and develop lots of exciting, new, reliable, interesting, challenging benchmarks. Thank you.
Thanks, Chris, for that great talk. Yeah, I mean, that was a very informative talk, actually. So we have several questions. I mean, if you see, there is a Q&A button or icon below, you might see.
Sure. So should I just go through them?
Yeah, I mean, sure. I mean, I can read them out if you prefer, but maybe if you just go through them, that would be.
Sure. I'm sorry, I'm losing my voice a little bit. Let me just cough for a second. So the first question I see here is there any specific advantage to using Roberta instead of BERT? There may well be. I think for many tasks, Roberta has proven to be better. But there still are differences among these transformer-based models. And the question of advantages could actually be tied up with issues of efficiency, for example. So let me go back to my example here. You might be thinking about just raw performance, of course. But if you're thinking about things like memory and throughput and efficiency, then, for example, the larger models are going to perform less well than the smaller models, even though the larger models might be better on raw performance. And that's what I would encourage us to think about. Not whether in absolute terms one of these models is better or worse, but rather how they differ and how that might play into achieving the goals that we set for ourselves. Second question, in the specific case of sentiment analysis and perhaps NLU in general, can we say we could create adversarial data sets synthetically using a generative model that takes a vanilla sentence and emits variance by adding elements like adjectives, quantifiers, adverbs at the syntactic level, and more complex constructs like irony, sarcasm, puns, humor, emoticons, poetics, rhetorics at the pragmatic level? I love it. I think we should be thinking a lot about this because it could be very efficient and it could help us in a naturalistic way key into really challenging phenomena that we want our models to capture. The actual landscape of people trying this is a little bit rocky, with some of them proving too artificial and some of them actually working really well to develop better systems. So I think the answer is we should think about this because the winds are clear, but more innovation is needed to really realize the full potential of this approach. But I hope people pursue it. Third question, connecting with your comment on NLI models failing to solve negation examples. Does a model failing on an adversarial sample indicate lack of adversarial sample in data sets only, or do architectures have something to say there? Oh, I think architectures certainly matter. I can certainly, for example, imagine architectures that would fail to learn the monoticity property of negation that I mentioned. And so that might be a case where even though you give that model a synthetic benchmark that has an unambiguous learning target with lots of good coverage across examples, the model still fails. I think that's wonderful because then you could say, look, the data set supported it, the signal was there, but this model failed. And that's the kind of conclusion that we often want to reach because it's exciting to rule out a class of models. But the more worrisome thing is that we're actually misdiagnosing those failures as model failures when in fact it's a problem with the data. And synthetic benchmarks could help us clear up that question. So this is interesting. So question, for measuring human intelligence, we have IQ and others. For machine intelligence, we have the Turing test and maybe the Chinese room. So what's the future of benchmarks? So what I said about being multidimensional and being careful what you measure and all of that, that applies to humans as well, right? So human intelligence is highly multidimensional and any specific test will not measure all of those dimensions. And so we should be careful about saying that any one measure gives us everything we need as a way of ranking people or whatever. I hope we're not doing that. I hope we're recognizing the multifaceted nature of intelligence for humans. And then the exciting thing is to think about also pursuing that kind of multidimensional approach for models we develop. This is interesting. I didn't touch on this. Are there any data augmentation techniques that you can suggest for creating synthetic examples in order to create benchmark data sets? Yeah, augmentation is wonderful. This is kind of related to that earlier question. I do think we can think about augmenting in automatic ways, or maybe quasi-automatic ways. That's kind of what we did with the MoNLI data set, where the augmentation was partly automatic and partly relied on us checking the examples and making small adjustments. And that gives you a really interesting benchmark really quickly. And I think that could be productive. And we should, again, be thinking about data augmentation as a way to achieve more robustness and maybe also to find and fix problems in the models that we're developing now. Absolutely.
Great. Thanks, Chris, for answering all those questions patiently. And yeah, again, it was an absolutely wonderful talk.
Oh, that's very kind of you. I'm sorry I'm losing my voice, but I'm really glad I had the chance to do this. Thank you for all for the questions and this chance to interact with you. It was great.
Thanks. It was our honor to have you here. Thanks.